Good evening, my dear J Warriors. Welcome aboard to the Road series, which is the free YouTube series for all the JEE aspirants for 2025 and 2026 in pure English from the best teachers. And we are on to the chapter of current electricity, and I'm going to take up this high weightage, very important but also lengthy chapter into multiple parts because you need that depth and that width so that you can understand each and every single concept. In today's class, we are going to see current parameters like what is current density, drift speed, mobility, relaxation time, all these things. And then we are going to go to resistance and how the field plays into effect, and also what is the EMF and the different manner in which you can connect a battery in a circuit. All these things in this particular lecture for finding equivalent resistances or basically Kirchhoff's laws and all those things, that will be a separate class. Okay, so let's start this particular high weightage chapter. Let me tell you, not just J but every competitive exam you take, always this chapter is high weightage. All right, so uh, after this chapter we will be doing capacitors also, because capacitors is also there. Okay, we have completed electrostatic field, electrostatic potential, we have completed even Gauss's law and its applications in the previous lectures. In case you have missed any of the classes, please check out our playlists and our jungle book in case you are not aware of it. Okay, so as you're watching this video, I think even the jungle book should be there even in this particular session's description box right over here. So you can see jungle book right over here. So this is basically a single sheet where you will get every single detail, be it the chapters of every subject which are completed, the YouTube link, you don't have to check any playlists, PDF notes, as well as the DPPs. Everything you will be getting over here. Also for boards and other examinations also, like SRM, JEE, VIT, EEE, you will be needing it later on. All those videos will be put up right over here, including BitSat, which will be slowly start getting populated. Okay, so that is your jungle book, because our series name is Roar, like a lion. So where does the lion stay? In a jungle, right? So that's your jungle book. All right, so let's begin with the class. Hello Trisha, Uma, Nikhil, hello Anusha, hello Homdeep, hello Sai. Good evening, good evening, good evening. Yes, your captain is here, and this will also work for CBSE. Okay, my art, don't worry, you can always catch up with the class. Even in a live class you can go behind. That's the functionality of YouTube, that's how it works. Don't worry about it. Okay, so let's start with the most important thing, the basics of this particular chapter, and that is current. See, I'll tell you what, when when you have a stationary charge, that chapter name is electrostatics, but the charge starts to move, charge in motion, dynamic charge, that is basically going to constitute something called as current. So moving charges, so moving as in dynamic, this constitutes nothing but the electrical current. This is nothing but the electric current. Now, current can be of many different types. It could be current of water. Water current is moving. All right. So it could be the current of an air. Warm air is blowing from a chimney. So electrical current obviously is the current of the charges over here. Okay, those moving charges. That's why I mentioned the word charges. Now, if you happen to look at an imaginary cross-sectional area, just an imaginary cross-sectional area, okay, it could be of any shape and size, doesn't matter, but it's an imaginary or real, doesn't matter. This is some cross-sectional area. Okay, so this is basically some kind of cross section. Through this cross section, some charges might pass through it. Some charges might basically pass through this particular cross section. So the amount of charge which flows through it. So the amount of the charge that passes through that cross section upon the time which is taken for it, this is basically called as your electrical current. That is how you define it. This is called as your electrical current. As simple as this. This is the simplest definition of this. Now, if you want to write it in the formula sense, you can write it like this. Symbolically, it is nothing but I. It is nothing but how much charge has flown upon the time. But whatever this current you write, this will be nothing but your average current. If you want to write instantaneous current, then you have to differentiate Q with respect to time, which also means that if you are given a particular graph of charge versus the time, and that graph happens to be something like this, you just have to draw the tangent. Let's say it is theta. So the slope of this graph, which is nothing but the slope of the charge versus time, gives you the electrical current at that instant. So this is nothing but your instantaneous. Current. So all these are pretty much simple definitions. This was your average current. Also, you can see that one can easily shift dt on the other side. dq will remain on the right hand side. So therefore, dq will be instantaneous current multiplied by the time. You integrate both sides. What you will get over here is the total charge which has flown. Will be nothing but integration of current with respect to time from some initial time to the final time. So if I take nothing but, let me show it right over here. This is time, this is current, and this is a graph of current versus time. And I basically take the area under the graph. Till certain time. That area under the graph gives me the how much charge has flown. So this is nothing but your area under the current versus time. This is very similar to position and velocity, guys. Velocity was rate of change of position, and when you integrate it, the displacement is area under velocity time graph. That is how derivatives and integration works. They are exact reverse processes of each other. Derivatives is always associated with slopes, and integration is always associated with areas. Is that right till this point? Yes, Deepak, Tatva is good enough. Okay, after watching my classes, Dash, check out my strategy video on how to score 99.99 percentile, number one. Number two, I would suggest you to read the theory from your textbook. Number two, after that, solve examples. Number three, after that, slowly grade yourself up, level yourself up from easy questions, substitution questions to slowly more difficult questions. Then go to mains PYQs, then go to more difficult questions, then go to advanced PYQs. In the end, you can make your own notes. Don't make your notes in the sheet. Okay, that is what you should be doing. And if you find difficulty in any concept, rewatch that particular concept video, or read the theory again from your textbook or some other resource also. Okay, that's what you need to do. Yeah. All right. Now going ahead, guys. Obviously, the unit of current will be nothing but ampere. Or dimension wise, it is just a raised to 1. Also keep in mind, it is a fundamental quantity. A lot of people think charge is fundamental. No, it's a fundamental quantity. Okay, charge is a derived quantity. Also, it is a vector or scalar. No, it is a scalar. And this is very, very important. Even if it has direction, and the reason for that is it doesn't obey it doesn't obey vector rules. All those vector addition rules, it basically doesn't obey. That is why it is a scalar quantity. Keep this in mind, right? As simple as that. There are many questions where instead of just charge by time, that charge might be also written down as number of charges into each charge, which is E, the whole thing divided by time. Some places you might need this. What is this E? E is nothing but your standard constant, my dear students. E is nothing but your standard constant, my dear warriors. Yes, it is 1.6 into 10 to the power minus 19 coulomb. 1.6 into 10 to the power minus 19 coulomb. How many charges exactly cross through it? That can be calculated using this formula. Charge is number into each charge. Each charge will be 1.6 10 to the power minus 19. You multiply 10 times, you will get the total charge which has crossed in that time t. That is what you will get. Also keep in mind one last thing over here. Current direction. The direction of the current, very, very important. The direction of the current is same as of positive charges, or you can also say it is opposite to the flow of negative charges, so that is the direction of the current. So for example, if there is a proton or there are many protons like this, and these proton beams are going like this proton beam is going like that, so the current will also be in this particular direction. Similarly, imagine there is electrons which are going like this in this particular direction, they are moving in this particular way, then the direction of the current will be exactly opposite. It will be in this direction, because if negative charges goes there towards the right side, it's as good as saying the positive charges are going towards the left side. So it's an equivalent statement. So this is something by convention for historical reasons. It's just which has been followed as a tradition. That's the reason why we are using positive. Or else you can question, why not, sir, negative? Okay, I hope this is absolutely clear. Everybody done till this point? Sai, if you spam too much, the admin will block you, bacha. So make sure you do not spam. Okay. All right. So all these things are done, and maybe we have some questions also lined up on this. Okay. An electron beam has a small aperture. Aperture is nothing but an opening. A total of these many electrons go through any perpendicular section per second. Find the current and the current density in the beam. Very nice question. Let's try to figure this out. Find the current is probably the easier part. Okay, then we can go to the next aspect of it. See, understand what is happening in this question over here. If you consider this as your cross section, which has an area of 1 millimeter square, I'll just call it as A, and electrons are flowing through it like this. Some number of electrons, a total of these electrons go per second. Okay, this is the number of electrons which go per unit time. I will call it as small n, number per unit time, small n. Okay, and in all of this, I have to find how much current is being flown through it. If these many charges go, how much is the current which is going through it? Fair enough. Now we all know that current is nothing but how much charge which goes per unit time. Also, I just told you some time back, it is also number of charges into each electron or each charge carrier's value, and this time will come as it is. But this n by t is already given to me, so I think we can easily find that out. So this n by t, this number of charge carriers per unit time, is given as 6 multiplied by 10 to the power 16 into each charge is 1.6 into 10 to the power minus 19. Is that right, my dear students? So this 16, 1.6 I can write it as 16 into 10 to the power minus 20. So 16 into 6, my dear warriors, right? So that is 96. And what else is there? The powers of 10. So that will make it 10 to the power minus 4. So that's it. That is the current. Current is 96 into 10 to the power minus 4 amperes, which is also 9.6 into 10 to the power minus 3 amperes, which you can also write it as 9.6 milliamperes. That is also fine. So 9.6 milliamperes. How many of you wrote it? Very good, home thief. Awesome, Anusha. Awesome. Vishal. Deepak, I think it should be enough. That should be enough. But there is nothing like enough because there is no limit to it. Whatever hard work you put, there is no end to it. If you feel that, okay, I'm done, sir, I think I'm doing enough, always think that there is always a room for improvement, okay? Because you never know. Maybe you are getting all India rank 2000, maybe putting in that next level of hard work, you will go to 1500. Maybe instead of getting some lower branch in some lower IIT, you are going to get a better IIT, better branch. So always push yourself. There is nothing like enough. Even if I say what you are doing hard work is enough, no, I'm not a good teacher. If I tell you what you are doing is very good, Shabas, awesome. You can rest now. If I do that, no, I'm not pushing you till the extreme. So push yourself even more. There is always something which you can do. And you will never regret, oh, thank God I did this. And now I'm here in this IIT. I'm getting this branch. All because I utilize every single bit of it. Okay? Cool. Whatever books you get, whatever papers you get, anywhere, you keep solving it. Now, what about the current density of the beam? Now, the density of any current beam, which will be in fact going to it in a bit, the density in such cases is how much current goes per unit area. That is called as the current density. That is basically called as your current density. The current, which we just got it as 9.6 milliamperes, the whole thing divided by 1 millimeter square. Okay, let's write it in SI units. So this is 10 to the power minus 3 amperes. Whole thing divided by 1 millimeter square. Milli is 10 to the power minus 3. Squaring it becomes 10 to the power minus 6. So this will become 10 to the power minus 6 meter square. So this will then become 9.6 into 10 to the power plus 3 ampere per meter square. That is your how much density is there. That is per unit area. As simple as that. Yes, that's the answer for it. So 9.6 into 10 to the power 3. Perfect. How about this JEE Mains 2024? This year's question. The current in a conductor is expressed as 3t square plus 4t cube, where I is in amperes, t is in seconds. The amount of charge which flows through the section of the conductor from 1 second to 2 seconds is. If current is given, charge is asked, that means you do not differentiate, you have to in fact integrate it. Remember, current to charge, you are going reverse. So the charge which goes through it is the integration of current with respect to time. The current is given as 3t square plus 4t cube, the whole thing dt. Time limit is from 1 second to 2 seconds, so that will be the limits of the integration. 3 will come over here. You will have t square dt. I'm opening up the brackets from 1 to 2 plus 4 will come over here. And then you will have integration of t cube dt from 1 to 2. Okay, so what is this? This will be 3. T square's integration is t cube by 3. T cube by 3. And I'll just put the limits 1 and 2 over here. 4. T cube's integration is t raised to 4 by 4. Limits of the integration over here. So finally, what do I get? This 3 and this 3 cancels. T cube is there over here. So put 2 first. 2 cube minus. Then put 1 over here. So minus 1 cube. That's the first term. Plus this 4 and this 4 cancelled. Put 2 first. So 2 raised to 4 over here. Minus. Then put 1 over here. So minus 1 raised to 4. So 2 cube is basically 8. Minus 1 is nothing but 7. Plus 2 raised to 4 is 16. Minus 1 is nothing but 15, guys. So hence the answer should be 22 coulombs. Hence the answer should be basically 22 coulombs. That is the answer. Yes, perfect. What a straightforward question. And this was asked in JEE Mains 2024. Hello, Santi. Very good. And guys, keep answering. I want everybody to keep answering the questions. Yes. And if you see in Tattva also, a similar question was asked. Okay, I'm not going to do this over here. you are going to put up the answers in the comments. So this is your homework. This is your homework, and the answer you're going to put it in the comments. Okay, and if you have tattva, you already know what the answer is, but don't look at the answers or the solutions. Try to solve it on your own. This is completely based. So that's why I say, if you are solving tattva modules, you're solving the PYQ questions, that's a very good practice. It's like you almost can crack mains like with a very, very good percentile or rank. Okay, so put it up in the comments so that I know that you are watching the lecture completely. Okay, great. Moving on to the next question on your screen. A charged ring having a charge of radius r is rotated. What is the current generated by it? Interesting question, my dear students. Let's have a look about it. So there is a charged ring, something like this. So that charged ring is like this. The charges are there everywhere. And what you're doing now is you're rotating it. You're basically rotating it with some angular speed omega. The total charge on the ring is capital Q. Question is, what is the current generated by it? Now, my logic to solve this problem is, all these charges are playing ringa ringa roses. Ringa ringa roses, pocket full of roses. Yes. Hello, Supriya, I'm very good. Okay. So, if you take any cross section, let's say somewhere over here, if you take a cross section over here, each of these charges will definitely flow through it. Each of these charges will definitely flow through it. These charges are flowing through a cross section anywhere you take. If you wait for one complete revolution time, then all the charges would have flown through it. All the charges would have passed through that imaginary cross section. So if I now talk about how much current is flowing, which is the total charge upon the total time, how about taking this t as capital T, which is now the time period, which is now nothing but the time period, and this is the total charge on the ring, the total charge on basically the ring. And is there a relation between time period and angular speed? Yes, circular motion 2 pi by omega, hence it is q omega divided by 2 pi. So that is the current, q omega by 2 pi. What an interesting answer. A rotating ring is nothing but, which is charged, is nothing but like a loop. This is like a loop carrying current. So you can often see this is just like saying I have a loop of current. This is nothing but like saying I have a loop of current. A loop of current. You will see in magnetism also this plays an important role, where this loop of current will produce its own magnetic field. And then this loop of current can also have its own magnetic dipole moment and all of that. So this becomes the basis of that problem which comes in magnetism. Okay, so this is the basis of that particular problem. All right. What are the chapters? Santosh, do one thing. Just check out my video which I had put up last month. Very, very important video on the entire strategy. Wait, let me just show it to you. This one. JEE syllabus in less time. Study related chapters together. I have given the correct order of the chapters plus which chapter of 11th you should study with which chapter of 12th. Because there are certain chapters if you study together you will cover in less time, and there is also a certain sequence of chapters. If you study this, it is better to understand that chapter, or else just because it is going on in your class, if you study it, that is not going to be efficient. So watch this particular video. It's just a 6-minute video. You can note down every point and start planning. Okay, that's what you need to do. Okay, how is omega in the denominator? Because that is a formula for time period. If you remember, what is the formula for time period? Time period is nothing but 2 pi divided by omega. That is what I've just substituted over here instead of the time period. Okay, so finally that omega will go on the top because it is reciprocal in the denominator, so it will go on the top. Is that understood? Okay, now let's go to the next concept, that is current density. All right, now Like I said before, in fact, in one of the H.C. Verma questions also, density of the current is how closely packed the charges are when they are flowing inside a wire. Imagine there is a corridor in your classroom or in your school or your coaching, and everybody has to go through the narrow corridor. And once the bell rings, everybody hurries to go outside the school or the college. Then I would say the density of all the Pandus and Champas, all the students, is very high in that corridor. But the corridor is very big. Aram say everybody can, take a lot of space and they can walk in that corridor. Then I would say the density of the students passing through the corridor is less. And if more students go in a narrow space, the density is more. So that is exactly what current density is. It's how many charges and how much current flows closely packed inside the wire of certain cross section. So it's the current per unit perpendicular area in a region surrounding that point, and it is a vector quantity whose direction is same as the direction of the current. Let's understand it better right over here. So like you can see over here, the current over here is probably going to go this way because the electrons are moving in the right direction. So the current will be towards your left side. The current will be towards your left side. There is also some area associated over here. There is also some area associated over here. Let's say we call it A. Let's say we call it as A, which is flowing through which the current is flowing. So if I divide both of them, what I get is current density. The symbol for that is usually capital J. This capital J, which is current density, is nothing but how much current flows, how much current, which is basically I flows, upon the area of cross section, upon the area of cross section, which is basically your A. Now, the unit of current density is obvious. It is nothing but ampere per meter square. Secondary thing, it is a vector quantity. Be careful about it. It is a vector quantity, same as the direction of current, same as of the current, same as the direction of the current. That means if current is here, even the current density vector will also be over here. This is where the current density vector will be. And dimensionally, this will be nothing but ampere is there on the top per meter square. So length raised to -2. So that is the dimensional formula of the current density. Now, you might be wondering, is there a vector formula, sir, for this? Is there a vector formula for writing the current density? The answer is yes, and let me show that to you as well. See, if you take area on the other side, area can be also treated as a vector quantity, and you have seen that in which law? In which chapter? Just in 12th. Yes, you have seen that in Gauss's law. Do you remember it, my dear students? My dear lions? Everyone? Do you remember this? Current can be also treated like, area can be also treated like a vector quantity. So you move it around, and what you will notice is that the current will be nothing but the current density dot product. It's a scalar quantity, that's why I'll need dot product with the area vector. So this is the vector formula for current density, which you should know. It is J dot A. It is dot product because current is a scalar quantity. Remember that. Area can be also treated like a vector quantity. So if by chance your cross-sectional area is some weird looking area, doesn't matter. Let's say this is your weird looking area. So the area vector will be in some weird direction like this. Remember, area vector is always perpendicular to the actual given area, and the current is flowing rightwards. So maybe the current density is like this. So you take the dot product of both of them. What you will then get is how much current is flowing through it. What you will then get is how much current is flowing through it. Is that okay? So this is the vector formula for current density. Keep that in mind. Okay. Moving now to the next thing. Let's talk about drift velocity. By definition, it just says it is the average velocity of, all these charged particles which are moving inside a conductor because of some electric field. That is by definition, but what exactly happens, I will show it to you in a very interesting manner. Just imagine, my dear students, let's take a conductor. Let's take a conductor. What is this? This is nothing but your conductor. This is your conductor. Inside this conductor, there are protons, neutrons, electrons, basically atoms. But out of them, only electrons are the ones which are mobile, meaning that they can move. Protons and neutrons can't leave their original places because they are stuck to that particular atom. Obviously, if the protons and the neutrons move, that will cause nuclear reactions, which is not what we are studying right now. Number two, the most mass of the atom, 99.99%, is concentrated at the nucleus, and nucleus is made of protons and neutrons. So understand, the protons and the neutrons, basically the nucleus does not move. Not just that, in fact, most of the electrons also do not move. The electrons which are tightly bound close to the nucleus, they are held properly. Okay, it's only those electrons which are a little bit far away, they can move around. It's like saying, when the teacher is in the classroom, all the people in the front bench, they cannot leave the classroom so easily. But imagine a student sitting far away, near the door, behind. When the teacher turns around, easily that student can, run out of the classroom. So those are the loosely bound students who can easily travel here and there. So same way, in an atom also, there are electrons which can easily move around. They are loosely held, and those are also called as your free electrons. So let me represent those free electrons with these negative symbols over here. Okay, something like this. Now, what happens is, when this conductor is not connected only to anything, it's like just this pen, isolated. Nothing is connected. So basically, right now what we have is an isolated conductor. Isolated conductor. These electrons will keep moving randomly here and there. These electrons will keep moving randomly here and there. Once this will move here, then it will move here, maybe then it will move here. I don't know, somewhere or the other. Maybe this moves here, then after that it moves here, then maybe after that it might move here, and then it might move here. God knows. Maybe this moves here, then this moves here, like this. Okay, and then this moves here, and then maybe it moves like this. Okay, this might move like this, then it might move like this, then it might move like this, and then it might move here, and then again maybe it moves here. So some random motion can be observed. So this is basically the random motion of the electrons, and this is due to the thermal energy. Due to thermal energy. If you increase the temperature, the number of collisions, the speeds, etc. will change. More atoms will vibrate, more electrons will be knocked out, their speeds will increase, collisions will increase, etc. So that is your thermal energy of that conductor. So if I ask you, what are the typical speeds of these electrons? The typical speeds of these electrons can be anywhere between 10 to the power 3 to, let's say, 10 to the power 6 meters per second. It's a range of speeds, like thousands of meters per second to, lakhs of meters per second. That's what the typical speed ranges are. But in spite of these heavy speeds, in spite of such large speeds randomly oriented, you will see that their average velocity, how much do you think it will be? That average velocity will be 0. And the reason for that is because since there is no net current, there is no net flow of current, neither the charges are going right side, nor the charges are going left, nor they are going up, nor they are going collectively down. If 5 charges go towards the left, 5 charges are also going to go towards the right at some or the other given point of time. So on an average scale, There is no net motion. If there is something which is going up, something is going down after some time. So on a larger scale of time, on an average, you will see there is no net flow. I hope this is clear. Hello, Tirthankar Mandal. Welcome aboard. Yeah. Till this point, is this clear? Everybody, absolutely. But now it is no longer isolated conductor. Now this conductor is now basically connected to a battery. It's connected, conductor connected to a potential difference. To a potential difference. Let's say this is at high potential. This is, let's say, at high potential. And let's say this is at low potential. Quickly think and tell me what will come between those potentials, high and low. Is the electric field. Yes, if you thought about it, very good. It's the electric field which is going to come, and electric field always goes from high voltage to the low voltage. So inside the conductor, this is very, very interesting thing. You will have an electric field which is set up. Inside the conductor, you have an electric field inside the conductor. If you remember the previous chapter of electrostatics, inside a conductor, the electric field used to be zero. Recollect. No electric field line can cut through a conductor. Inside the chunk of that solid part of the electrical conductor, the field will be zero. All the points are equipotential. But here I'm saying inside the conductor itself, there is voltage difference, and that's why there is electric field, and that's what causes these electrons to move. Remember, the previous chapter name was electrostatic. Stationary charges. Charges are no longer flowing. That's where current is zero, field is zero, voltages are same. But electrodynamics, current, electricity, there is voltage difference, there is electric field, and there is flow of charges, which in fact makes up the electrical current. Is that clearly understood? Major difference. Very, very important. I hope this is absolutely understood by everyone. Now, because of this electric field, what will happen is as follows. Observe this carefully. Imagine this electron was going to hit here and maybe going to go like this. Instead, now what it will do, because of the electric field, it will experience a force. Which direction will it experience the force? Towards the left side. Why? Because it is negative charge. So the force will be towards the left side. So the actual path taken by it, will be probably something like this. Maybe it will go here somewhere. This is the actual path. This is nothing but the actual path. The red one is the path without the electric field. This is the green one is the actual path with the field. This is with the electric field. Oh, interesting. And this is also true for every single other motion of the charge. So another charge was going like this and it was going like this maybe. Okay. Or another charge was probably going here and then going like this maybe. Another charge was maybe going here and then going like this maybe over here. So their motion gets affected because of the field applying a force. So that force will try to pull it over here. Maybe it will go like this. Maybe this will make it go like this, and maybe it will come over here like this. Maybe this will go over here like this, and maybe this will go over here like this. Something like that. So you can see at every single place there is some displacement of the charge overall. So you can see the charges have displaced over here after some time. The charges have displaced over here after some time. They have displaced over here. So they are displacing slowly. So this is basically they are drifting. So I would say the charges drift. The charges drift due to the force by the field, due to the force by the electrical field. Do you see that? The charges are slowly going towards one particular side because of the force acting on those charges. And the force, remember, on all the charges, electrical force is this way. That force magnitude wise is charge multiplied by the field. The force is towards the left side because it is a negative charge, or else on the positive charge it would have been on the right side. This exactly makes up the current. That is why the charges will start going towards to this particular side, and that's the reason why you will have current in this particular, no, sorry, not in this direction, in that particular direction, because negative charges are going here. So current will be in this particular direction. So you'll have electrical current. Hence, current flows in the direction of the field due to the net movement. Now quickly think and tell me, is the average velocity going to be zero or not in this particular scenario? In the previous scenario, on an average, these electrons, on an average, one will move here, one will move there. On an average, the velocity was zero. In this particular scenario, do you think the average velocity will be zero? No, right? In fact, the average velocity will not be zero due to the drift, due to the particular drift and that current. This average velocity in this scenario is then called as the drift velocity. What is this called? That is called as your drift velocity. Drift velocity. How quickly are these charges drifting with time? And these drift velocities are in micrometers per second to few millimeters per second. Millimeters per second. Okay, that's how small they are. They are not very large. Don't expect, sir, in a wire which carries current, sir, the electrons move at 100 meters per second, sir. No. 1 meter per second, sir. No. It's not that high. It's very, very, very slow. Yep. Now tell me one thing. When you turn on a bulb, okay, when you turn on a bulb, say for example, this is your circuit. This is the bulb. The wire goes here. There is a switch here, and there is a battery. Say like this. Imagine you turn this on. You turn this switch on. Do you think the electron which is over here immediately reaches here? Immediately? If not, how does the bulb turn on immediately? What is happening? Because I know that the speed with which these electrons drift is very less, millimeter per second. So if the wire is 2-3 meters long, it's going to take couple of seconds for that electron to reach on the other side where the bulb is, and then it has to flow through it, and then the bulb will glow. But that is not the case. The reason is the moment you turn on, it's the electric field. It's the electric field that travels at the speed of c, at c speed, which is the speed of light. Almost instantly it reaches everywhere and it informs. Imagine it's like Flash, some superhero going through this entire circuit, zoop, and telling everyone, or distributing pamphlets, throwing pamphlets. Hey, start running, start running, start running, start running, start running, start running. Who is it distributing pamphlets to? The electrons. All these electrons get informed and they start moving with very slow speed. Zoom. They'll move with very, 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 very low speeds, few millimeters or micrometers per second. And that is exactly what makes up that current. Okay, so that's how the bulb glows almost instantly. That's how the bulb glows. The bulb glows instantly. Keep that in mind. So a lot of people have this particular doubt. Okay, great. Now, How much is the value of this particular drift velocity? Let's also have a look at it. How much is this value of this particular drift velocity? Okay. So imagine you take a cross-sectional area A of length L, and each of these electrons or these charge carriers have a drift speed of Vd. Okay, each of these electrons or these charge carriers have a charge of E. The average velocity is Vd. D stands for drift. And let's say I give you a number called as small n, which is how many number of charges are there, how many number of charges are there per unit volume. How many number of charges are there per unit volume, which is given by small n. Now this small n can be calculated if you know the density, molecular mass, and if you know how many charges are there per atom, etc. Maybe copper might give 1 electron in contribution um, as a free electron. So in 1 mole, how many copper atoms are there? So each copper atom is giving 1 electron free. So in 1 mole, 6 into 10 to the power 3 electrons are free. And we know the molecular mass of copper. So then we can calculate how much, how many number of electrons are there in 1 meter cube of copper. Okay, so that calculation can be done, or maybe it is already given to you. Most of the times it is given to you. So how do I relate all these numbers with each other? So first of all, I start off with the definition of current. First of all, I start off with the definition of current, guys. So current flowing through it is the total charge by the total time. Total charge by the total time. Everybody with me? Yep. So can I write charge in terms of some other variables over here, in terms of E maybe? In terms of E maybe? I think so. I can write it as total number of charges into E, the whole thing divided by time. But remember, capital N is the total number of charges. So that is basically capital N, the total number of charges present in this conductor. How much is the volume? Well, the volume was area into length. Volume is area of cross section multiplied by length. So therefore, capital N will be AL small n. Capital N will be area of cross section length into small n, and the rest of the terms as it is E divided by basically T. E divided by basically T. Is there something that we can do over here? Just think about it. Is there something that we can do over here? Length by time. The distance that you travel in how much time, that is your speed. Oh, yes, sir. We got now. What is it? It's A. You take L divided by T separately, N and E. So this will then become A into what is this L by T? It is nothing but your drift speed. It is nothing but your drift speed. So I'll just put Vd over here, and I will just put N over here as it is and E. That's it. So I've got a formula, and let me write it down in a very simple way. I'll write N first, E over here, A over here, current over here as it is, and Vd over here. The reason why I wrote it down like this is because one of the most famous companies, which is even valued more than Apple these days, is Nvidia graphics card, right? They are making amazing chipsets for your artificial intelligence to work. So Nvidia, one of the top most companies in the entire world, bigger than Apple, Microsoft, Google, Facebook, Meta, you name it. It's bigger than that today. So Nvidia, that's how you can remember it. Yep. Also, you can rearrange this formula to make it look slightly different. And how? Observe it carefully. Shift that area below. What you will get is current by area is equal to N, and then you have Vd and Ea. Oh, wait a minute. What is this? What is this current by area? That is nothing but your current density. That is nothing but your current density, guys. Yep. So J will be equal to N Vd into E. There is no area there. Area has been shifted below. Another thing interesting is if the drift velocity is towards the right side, that means electrons are going towards the right side, current will be going towards the left side, that means even the current density will be in this direction. Current density will also be in this particular direction. Is that right? Everybody with me? Okay, but E itself might be negative because electron charge will be actually minus 1.6 etc. So if you write it in vector form, this will be J bar, this will be Vd bar. J and Vd are actually opposite of each other. Observe, J is opposite of your drift velocity, but because E itself can be like negative 1.6, the actual charge into 10 to the power minus 19. Okay, so that's why I don't have to put an extra minus sign. So this is then the vector equation of this. This is the vector equation of this. So you can put it in vector form also. Let me just put it over here. So J is over here. So J will be equal to here N, and then I will put Q over here. This Q can be your itself negative charge. Q can be your negative charge, and this will be your drift velocity, and this will be your current density. So this is another way of writing it. Another way of writing it. J is equal to NVD into the charge which is actually moving. The charge which is actually flowing. The charge which is actually flowing. In this case, it is the electron. Is that clear? Everyone? Yeah, we'll come to the mobility formula, etc. in a bit, but not now. Hold on for some time. Okay. Now, there is also another formula for drift velocity, and that is also something which you should know. So, remember, just some time back, I told you there is electric field which is set up, because of which there is a force acting on every single charge, and these electrons begin to slowly drift from one side to the other side. They start to drift from one side to the other side, which makes up the electrical current. So there is another formula over here, just like you have your equation of kinematics, which looks like V is equal to U plus acceleration multiplied by time. Every electron, what happens is, once it hits another atom or some another object or another particle within that conductor, it might lose all its velocity. Then that force will accelerate it, and it will achieve some really good speed before it again hits and again loses all the velocity. And this process continues. And if it didn't continue, there would be a big problem. Imagine inside the conductor, because of the battery or the voltage difference, the field continuously applies a force, and that force continuously accelerates the electron. That means after a few seconds or after a few minutes, the electron will reach very, very high speeds, which is not found. So why is the electron not continuously accelerating? It's because it is meeting some people. It is colliding with something. It's losing its energy some places during the thermal collisions. So that's why it accelerates. It accelerates. It hits. Zoop, loses all the speed. And then again it slowly picks up the speed because of the force, accelerates, and again hits, and again loses all the energy. And again it accelerates. So this keeps on happening. Zero velocity, maximum speed, zero velocity, maximum speed, and there is a time gap between these things. That time gap from one collision to the next collision where it loses all the velocities, that is called as relaxation time. That is basically called as your relaxation time. That's the time. I know you might think it is quite on the contrary. So that's the time when the electron is not colliding and it is accelerating. It's relaxing by accelerating, and when it collides, it faces a big slap on its face. It gets hit, so it's hurt. It's hurt, and then again it gathers all that energy because of the force, and it begins to accelerate. So it's relaxing, it's regenerating, it's refreshing when it is actually moving. Understand that. That is why it is called as relaxation time. And that's why you get the formula over here as it is over here. Vd is equal to, initial velocity will be a big fat 0, plus acceleration is nothing but your force divided by mass, and this time that you see over here, I will put it as tau. This is called as your relaxation time. This is called as a relaxation time. That is the time interval, that is the time gap between collisions when it is at rest. So it starts from rest, accelerates, starts from rest, again accelerate. That's what it keeps doing. Now this force, I can also write it as the charge multiplied by the electric field. So this will come over here as it is, and this tau over here as it is. And what you get over here is the drift speed. So this is also a very, very important formula. This is also a very, very important formula. Drift speed is E tau by m, tau being the relaxation time. Is that okay? All right. Sanjay, I've already made a video for it. Please check it out, bacha. Full syllabus, less time, study related to 11 chapters together. Complete thing over here. Also, I have put up one more strategy video in the live part. I think it should be there. Okay, just go little behind. I have given month-wise plan also. I have given month-wise plan also. Long time back. Few weeks back. See, proper. How to complete the portion, proper roadmap and strategy and plan is given over here. Please check it out. Okay, it's there. Fair enough. But if you want me to make another fresh video, I'll make that also. Don't worry. All right. So with this, let's move ahead and let's start with some questions. Here is the first question. Calculate the drift speed of the electrons when 1 ampere of current exists in a wire of area 2, number of free electrons in 1 centimeter cube of copper is this much. Calculate the drift speed. Let's write down the formula of drift speed. Vd, current, is NVDA. NVDA, perfect. Current given to me. N not given directly, but I can write it down. Area, yes, E standard value. So the current value is 1 ampere. This N is capital N by volume. So what is capital N? It is the number of charge carriers, which is 8.5 multiplied by 10 to the power 22. What is the volume? 1 centimeter cube. 1 centimeter is 10 to the power minus 2 meters. So cubing it means raised to the power 3. Drift speed, I do not know. Electron charge 1.6 into 10 to the power minus 19 multiplied by the area. What is the area of cross section? 2 millimeter. Milli is 10 to the power minus 3. So square it. 10 to the power minus 3 whole square. Wow. That's it. Guys, you just need to rearrange these numbers and you will get the answer for the drift velocity. Is that okay? Everything is known to you now. Everything is given to you. Cancel the powers. Whatever calculations are required, you do it. And just check out the answer. If you get it as 0.036 millimeters per second. That's so less, guys. 0.036. Wow. 0.036. So it will be like 36 into 10 to the power minus 6 meters per second, which is basically 36 micrometers per second, which is also 0.036 millimeters per second. Like I said, drift speeds are typically in the ranges of micrometers to millimeters per second, typical ranges. Okay, so that's how you calculate it. Is that right, everyone? Shall we go ahead? Okay, let's go to the next question on your screen. The current density is this much. The cross-sectional area is this much in the YZ plane. Then how much current is actually flowing through it? Oh, wait a minute. I know the formula for current density and area. Current is current density dot the area vector. The current density is already given. It is 3 I cap plus 4 j cap. But what about the area vector? Area magnitude wise is 2, but it is in the YZ plane. So let's understand it. If it's in the YZ plane, this is Y axis, this is your Z axis. The area vector area vector will be perpendicular to it and it will be parallel to the x-axis. Oh, so this will be 2 cap if you consider the direction. 2 cap considering the direction. So that's it. We know I cap only multiplies with I cap. J cap does not go with I cap. The dot product is 0. So hence the answer should be 6 amperes. Hence the answer should be 6 amperes, which is B for IIT Bombay. Yep, that is the correct answer. Very good. Excellent. Moving to the next question of mobility. Yes, mobility. Say, have you seen, like, if somebody is very obese, very huge, and imagine a class full of obese people and they are asked to run inside a corridor. Maybe there is a fire in the classroom and everybody has to exit the classroom, then through the corridor, then through the staircase, and then outside the school premises. Imagine all obese people, big people like this. They will need so much of space. There will be a lot of pushing, there will be a lot of heckling, there will be a lot of commotion over there. But imagine very slim people, okay? Zoop, they will come out. They are very mobile. That's exactly what happens inside a conductor also. It's not got to do with the sizes though. Don't think one electron is big, one electron is slim. No, all electrons are of same size. But it depends on the material tendencies to hold that electron. There are some elements, maybe like aluminum, they do not let those electrons move around freely. But copper, better conductor than aluminum. Gold, even better. They are like, electron, you want to go? Okay, go. Fine, no problem. So they are very mobile. So it depends on the material characteristics. It might also depend on the temperature and other parameters. But how easy it is for these electrons to flow when you connect it to a potential difference. How easily they can flow when you connect it to a potential difference. And what does potential difference create? It creates electric field. So for a given field, how mobile these charge carriers are is basically your mobility. We all know that the drift speed of an electron, okay, is going to be nothing when there is no field, but with the electric field, it has some drift velocity. So that's how mobility is also defined. So mobility, the symbol is mu. Mobility, the symbol is mu, is nothing but the drift speed, per unit electric field. That's it. That's the formula of mobility. That's the formula for mobility. Drift speed per unit electric field. How quickly the electron can move through a conductor, semiconductor, does not matter. Okay, for a given amount of electric field. As simple as that. Yep. Great. Awesome. Yeah, laws of motion will come later on. Yeah, don't worry about it. Laws of motion, everything will do. Okay. Are there different ways of writing mobility in terms of different things? The answer is yes. See, guys. See, mobility was nothing but, just like over here, drift speed per unit electric field. I can always write our drift speed as I is equal to NVDR. Okay, or I can also use drift speed is E by M into tau. Both the options are available with me. So if I use this formula, then what will happen to our mobility? Mobility will be 1 by E as it is. Instead of VD, I will put it as current divided by NEA. That's what I will write. And if I write it over here, then the mobility will be nothing but 1 by E as it is. Instead of drift speed, what will I put? I'll put E tau divided by M. Best part is E will cancel. E will get cancelled and I will be left with E tau by M. That becomes your mobility. Generally, many questions also use this formula. No need to by heart this, but I'm just telling you, you can substitute any of the old formulas or the previous formulas over here instead of drift speed. Okay, you can use that. Also keep in mind electric field. Electric field is nothing but voltage difference divided by the distance that you travel, that is the modulus of it. So if you know the voltage and you know the how much distance is there between that voltage, dV by dr is the field, you can also substitute the electric field over there. Is that right, everyone with me on this? Great. So keep all these things in mind, okay? You don't have to by heart any of these things. This is the main formula which you need to know. But apart from that, you should know that it can be transformed using prior knowledge of electrostatics or drift speed, whatever you have learned. So oops, I showed the answer by mistake. Just see this question. A charged particle having certain drift speed in a field of this much has a mobility of. Guys, what is the formula for mobility? I just told you it is drift speed per electric field. Drift speed is already mentioned as 7.5 10 to the power minus 4 upon the electric field is 3 into 10 to the power minus 10. 7.5 and 3, guys. Come on, what is the answer going to be? Yes, it's going to be 2.5. Yep, into this will become 10 to the power 6. So is it there somewhere? Yep, it is there as option number D. It is there as option number D. Very straightforward question. These kind of questions also do come in the examination. Hello, Ritishri. Duration of this session, I think more half an hour or something, not more. Yeah. Okay. Next. And remember, guys, very, very important. Let me remind you that these sessions are not one-shot sessions. These sessions are not quick sessions. These are not revision sessions. We go from the basics to the high level, right? This is what road series is about. These are in-depth classes for all the kids, all the students who want to understand all the concepts properly. If you are looking for revision, this is not the right time also. Plus, this is not the right series also for revision. For revision, it has to be very quick, which we will do later on once the syllabus is complete. But for that, first, let's complete the row series, right? Okay, the relaxation time is doubled, field is halved. In a conductor, what will happen to the mobility? If you can answer this, I'm really proud of you. Guys, spam the answer in the chat box. Spam the answer in the chat box right away, right now. Yes, think about it. What will happen to the mobility? I think I just gave you the formula for mobility in some other terms. E tau by m. E tau by m. Mobility was E tau by m. The relaxation time is basically doubled. This quantity is basically made 2 times. If it is made 2 times, E and m is not changed. Obviously, this should also be made 2 times. Then you might be wondering, sir, what is the use of the electric field is halved? No use of this. There is no use of this. Hence, the mobility will be also doubled. Yes, that is the correct answer. A lot of people are going to get confused over here thinking about the electric field. And I have seen many people doing this also, where, right, mobility is drift speed by E. So many people have seen doing this. Sir, the field has become half. Sir, the field has become half. So that 2 goes on the top. So that's why mobility will become 2 times. That is wrong because you do not know what will happen to the drift speed. Will it stay same or not same? We do not know that. So in fact, what about the drift speed? We do not know. So this is not the right method to do this problem. This is the correct method to do this problem. Because what happens to the drift speed is not even mentioned, or you have to calculate it via some other way. Keep that in mind. Okay. Moving on now to the main thing, which is Ohm's law, definition of resistance, resistivity, conductivity, conductance, temperature dependence of resistances, right? Geometrical aspects, and obviously the EMF. So let's come to that Ohm's law part. Okay. Now, what Ohm did long time back was he used different materials. He connected it to different batteries. He checked the voltage across it and he saw how much current is flowing. And then he saw a very simple linear relationship between how much voltage goes, how much current flows and how much voltage has been applied. And he saw that it was linearly proportional. So the applied voltage on a conductor is directly proportional to the current which is passing through it. If you apply more voltage difference, more current will pass through it. That's what he simply saw. But that is the crude form of Ohm's law. In fact, Ohm's law gives us the definition of something called as the resistance. Think of it like this. This Pandu is called V, voltage. This Pandu is called Ohm, basically resistance. This Pandu is called A, which is basically current. Voltage, which is who gives it? Battery, a cell, external supply. The battery gives some voltage. It is giving that push. The resistance blocks that flow, blocks the current as much as possible. More resistance will block it more. This Pandu is that electron, the charge carrier, which is going through that pipe. So the battery pushes the charges to flow inside the conductor, and the resistance opposes that particular flow. So resistance is the opposition, is the measure of the opposition of the flow of the current inside a conductor. If it's a bad conductor, it has high resistance. If it is a semiconductor, it has decent resistance. If it is a very good conductor, it has extremely low resistance. If it has infinite resistance, that means it will completely block it. That means there is no opening here. You have tightened it so much, no current can flow. And if the resistance is perfectly zero, then it's a superconductor. That means there is no resistance at all. You don't need any push. Once the push is given initially, zoop, the current will keep on flowing. That happens, by the way, at 0 Kelvin. Let's not talk about it today. I'm so glad, Avanishri VP, you scored centum in your school through the live classes over here. Awesome. Really proud, Avanishri. You are a regular student, and I'm so happy for you. And this also shows to other students why you should be very regular in the classes. You can give many excuses, but if you are regular, you will do well. I'm so proud of you. We, the three, maybe around 2 to 3 classes. Okay. Great. So let's have a look at the Ohm's law over here. What Ohm saw was, for different conductors, the graphs look like this. For different conductors, this is how the graphs look like. For, let's say, conductor 1, for conductor 2, etc. So for these conductors, the voltage difference was directly proportional to the current which flows through it, and that constant of proportionality was called as R, which is nothing but your resistance, which is nothing but called as your resistance. So this is the basic way of writing your Ohm's law. But remember, this is only valid for whatever I have written over here. That is basically for ohmic devices. Ohmic devices. Ohmic devices are like resistors or wires, basically conductors, etc. There are many devices which are non-ohmic in nature, and for them the graphs might look like this or might look like this. Okay, these are basically non-ohmic devices. Non-ohmic devices, you will see the voltage is not proportional to the current. Very important. It is not proportional to the current. It could be some weird function. Here it is constantly proportional. So this resistance is constant. Here you will see that the resistance will not be a constant. It will have variable resistances for different voltages. That's what happens in semiconductors. The best example for non-ohmic devices is nothing but semiconductors. We will see it in a separate chapter. Semiconductors are non-ohmic devices. In this chapter, we are studying mainly ohmic devices where the resistance is constant, the slope is constant, voltage is always proportional to the current. The slope could be different for different conductors, but it is constant. That is what is important. V is equal to IR. The R is nothing but the resistance. It is measured in ohms, and you can see that the unit of resistance is ohm, symbolically this. which is nothing but volts and currents. So it's nothing but volt per ampere. Volt per ampere. 1 ohm is when 1 ampere of current produces a voltage of 1 volt. That is what ohms is. Okay, keep all these things in mind. Now, if you look at the slope of the graph, depending on whether it is voltage versus current or current versus voltage, looking at the slope, I can measure whether the resistance is high or low. Like particularly in this graph, if I see what the slope is voltage by current, y-axis by x-axis, so voltage by current, V is nothing but IR, I cancel, so it is basically R. So the slope is directly proportional to the resistance in this case. So the one which has more slope has high resistance, the one which has less slope has low resistance for a voltage versus current graph. So looking at the slope, comparing them, I can predict whether the resistance of this conductor, this wire, this resistor is high or low or medium. We can do that comparison. Okay, as simple as that. Everybody till this point? And the limitations of Ohm's law also, I have mentioned it to you right over here. Basically, it is not valid every time. It's not valid for semiconductor like devices which are non-ohmic devices. So I'm just not going to use this slide, just deleting it. Okay. Now let's see what does this resistance basically depends on. So say for example, if you have a conductor or a wire like this of area of cross section A, length L, I can depict it as a resistor like this. This is the symbol of resistance. This is your symbol of resistance. It offers some resistance, that's the symbol of it. This resistance is found to be directly proportional to the length. It's also found out to be inversely proportional to the area. These are all experimental results. Via experiments, there is no proof for it. So therefore, the resistance will be proportional to length, inversely proportional to the area. The constant of proportionality, I will call it as rho. The constant of proportionality, I will call it as rho. That rho, which you are seeing right over here, is called as resistivity. Resistivity. This resistivity depends completely on the material. It depends on the material. Like for copper, it is very less. For copper, it is very, very less. But for maybe some other object, maybe like rubber, which is a very, very bad conductor, it will be very, very high. Okay. So for plastic, it's very high. So bad conductors have very high resistivity. Good conductors have very low resistivity. That is what it depends on. It also depends on something called as temperature, of course. We'll talk about it in the next slide. Temperature. So in all, resistance depends on the temperature, the material, whether it is copper, aluminum, silver, gold, plastics, silicon, germanium, etc. It also depends on the geometrical aspects. So like you can see over here, both these things are nothing but the geometry of the conductor. The geometry of the conductor. All these things together define the resistance. Resistivity does not depend on the length. A lot of people think, sir, if length increases, resistivity decreases, huh, sir? No, if length increases, resistivity does not change. Resistivity only depends on the material and the temperature, nothing else. So in fact, rho will still be the same. If length increases, resistance will also increase. Keep that in mind. Okay, very, very crucial. All right. Now, what is the unit of resistivity? We can talk about that as well. It's not that difficult. See, this is meter square. Meter will cancel, 1 meter will remain here. Take that meter over here. This is ohm. So the unit of this will be ohm meter. Ohm meter. Okay, as simple as that. Perfect. So that is what resistivity is. Resistivity is a material and temperature specific quantity. It does not depend on the dimensions, and it's basically going to give you a measure of how good or bad the particular wire is. That's all. Now, resistance we have already defined. All these things are done. Okay. temperature dependence on resistance. How does resistance change with temperature? Well, see, let me tell you what happens. Let me tell you what happens. When you increase the temperature, the molecules, the electrons gain a lot of energy. They have a lot of speeds. So they will collide more. So an electron, which could pass very easily through the gaps between the atoms and without colliding too frequently with other electrons, now will collide more frequently, and the gaps will be reduced because now these atoms, these molecules are shaking. They're obstructing the path. It's like too many dynamics into the picture. So when you increase the temperature, the speeds increase, the gaps reduce, the frequency of the collisions increase, the electrons end up losing more energy, which causes a sense of higher resistance. So increasing the temperature increases the resistance, as simple as that. So for conductors, very, very important, for conductors, as temperature rises, the resistance also rises. In fact, the formula for that is resistivity at any temperature T is original resistance 1 plus alpha delta T, or you can also use resistance at temperature T is original resistance 1 plus alpha delta T. What is this? What is this alpha? What is this alpha? This is called as your coefficient of thermal resistance. Coefficient of thermal resistance. It completely depends on the material. It depends on the material. If this formula is very similar to coefficient of linear expansion, if you remember that chapter, L is equal to L naught 1 plus alpha delta T, but that was thermal expansion. This is temperature coefficient for resistance, slightly different formula, same but different. Okay, this alpha, if it is very high, that means when you change the temperature, the resistance changes rapidly. If alpha is very low, that means even when you change the temperature significantly, resistance is not changing so easily. So that is immune to the temperature changes a little bit. So if alpha is less, it is immune to the temperature changes. Okay. If alpha is very high, then it is very sensitive to the temperature changes, rapid changes of resistances. But keep in mind, these relations are approximate, they are not perfect. So these are valid only for a small range. It is not actually linear, it is not actually a straight line because these are looking linear. So you can see over here the temperature is changing from 200, 400, 600 Kelvin for a nichrome wire on an absolute scale. It is almost a straight line. But if you look at a semiconductor, it is a curved line like this. If you look at the temperature starting from 0, okay, for copper, you can see it is a complete curved line. Only for a small section, it is straight. Section, straight, straight. So it is straight for a small range, not for a big range. So usually when we get problems, we'll assume it is linearly dependent, but you should know that it could go out of the linearity. It will become non-linear if you change the temperature too much. Okay, so something which you should be very, very aware of. This is an approximate formula. Okay, hi Gunjan. Yep. Sarvana, I'm pretty sure next year you will have a story to tell from 83 percentile to 99.99 percentile. Yes or no? You will, right? Very good. Awesome. Lastly, conductivity. It's exactly opposite of resistivity, my dear students. So, conductivity is nothing but 1 by resistivity. So, this is resistivity. This is conductivity. This is conductivity. As simple as that. And you can also write one more relationship, conductance. Conductance is 1 by resistance. There are two different things. Resistance and resistivity, two different things. Conductance and conductivity, again, two different things. But relationship between these two and these two are very similar. More resistance, less conductance. less resistivity, more conductivity. Okay, their relationships are very, very similar. Okay, but they are two different things. That's what you should also appreciate. Keep all these things in mind. Obviously, in this case, the unit will be because the resistivity was ohm meter, this will be ohm inverse meter, as simple as that. Now there is one last relationship over here which you should also know for finding electric field and relating it with conductivity, etc. In fact, I think, yeah, we are directly starting off with problems. See, as per Ohm's law, voltage was current multiplied by resistance. So let me substitute the formula for resistance, which is nothing but resistivity into length divided by area. So that is what resistance is. Rest of the things as it is. V is equal to IR. Bring length below. Current is as it is. Bring that length below. Area is below here. And resistivity, leave it over here. What is voltage per unit length? Voltage difference per unit length, guys. In case of a wire, think about it. If you have a wire, whatever is the voltage per unit length, think about it. There is some voltage for this particular length. What is that voltage per unit length called as? Yes, it is nothing but your electric field. It is nothing but your electric field. Perfect. There might be some current flowing in the wire. There might be some current flowing in the wire that will also cause some current density. That will also cause some current density. Yes, what is that current per unit area? That is nothing but your J. That is nothing but your J over here, I by A. And that rho is as it is, that is resistivity. So E is equal to rho J is a very important relationship. In fact, in vector form, it is written down like this. E bar is equal to, it's a vector, rho is not a vector, J is a vector, E bar is rho J bar. This is the vector form of this equation, very, very important. E bar is rho J. E bar is rho J. Everyone, till this point clear? Absolutely. This can be useful for finding the electric field inside a conductor. You can also play around with it a little bit. Let me show you how. E is equal to rho J, right? E is equal to basically rho multiplied by J. Now, instead of rho, I can write it as 1 by sigma, which is basically conductivity. Instead of E, I can write it in terms of mobility. So remember, mobility was the drift speed per unit electric field. So basically, yes. So E will be Vd by mu. It will be Vd by mu. That is what it is. And J, I can just write it as current per unit area. Just check this out. Current per unit area. Perfect. So what will I get sigma as? Therefore, what will I get sigma as? Sigma, you can, sigma, I will get it as Vd is there over here. Okay. Yes, perfect. This fields for unit electric field. Okay. Sigma, okay, fine. I will get it as mu. Into current divided by area, and this will be nothing but your drift speed over here. So you can see you can get it in different forms if needed, whenever needed. Okay, whenever needed, you can obviously get it in whatever form you want. All right. So these are some different transformations which you can do, because you know the formula for mobility, you know the formula for current density, right? You know the formula for resistivity and all of that. Okay. Shall we go ahead now to solve some questions? More importantly, this formula, very, very important. Just like voltage, you have field. Just like current, you have current density. Just like resistance, you have resistivity. Very, very crucial, important looking formulas. Questions coming up on your screen. Here it is. Calculate the resistance of aluminum wire of length 50. Cross section this much. Resistivity is this much. Calculate the resistance, guys. Which formula do you use for the resistance? R is equal to rho L by A, right? So let's use that. R is equal to rho L by A. Resistivity is 2.6 into 10 to the power minus 8 ohm meter. Perfect. Length 50 centimeter is 0.5 meters divided by area 2 millimeter. Millimeter is 10 to the power minus 3. Square it. So that's it. This is what it is going to be. Now 0.5 is half. So this will be nothing but 26 divided by 4 multiplied by I just shifted the decimal. So this will be 10 to the power minus 9, of course. This will be 10 to the power minus 6, of course. So this will be nothing but 13 by 2, which is nothing but 6.5 into 10 to the power minus 3. What is it? Ohm. This is nothing but ohm. 6.5 into 10 to the power minus 3 ohm. Exactly the answer what we require. Okay. Very, very small resistance and kind of makes sense because aluminum is a good conductor. Aluminum being a good conductor, the resistance has come out to be low. If it was something like carbon resistor or something, it would have come out to be very, very high. Moving on to the next question on your screen. A wire is this much, area is this much, connected to a battery, current this much, resistivity is how much? Ooh, okay, resistivity is asked. I need to know the resistance then, but resistance is not given. But no worries, voltage is given, current is given. Using Ohm's law, V is equal to IR, current is 4, voltage is 2. I will get the resistance as 0.5 ohms. So now let's go to our main formula. Resistance is rho L by A. So rho is equal to RA divided by L. Resistance is 0.5. Area is 1 millimeter square. So 10 to the power minus 6 by length. Length is basically 0.5. So that will be 10 to the power minus 6 ohm meter. Ohm meter. 10 to the power minus 6 ohm meter. That is D for IIT Delhi. D for IIT Delhi. Yep. Thank you, Sam Cherry, for all the love from Telangana. Miru Ella Naru, Sanjay Garu. Yes. I hope you guys enjoy the classes, especially designed for all the students who want to learn in English medium with quality content. Thank you so much, guys, for all the love. Okay, moving on to the next question. The resistance of tungsten is this much at 133. What will be the resistance at 500? The temperature coefficient of tungsten is this much at this much. Okay, so use your thermal coefficient of linear expansion. Sorry, resistance. My bad, not linear expansion. All you have to do is RT is R naught 1 plus alpha delta T. Resistance at 500 is what is asked. So R500 is equal to original resistance is 133. 1 plus alpha, this is nothing but 0.0045 multiplied by temperature difference, 500 minus 150. So this is 500 minus 150. That's it. That is what you need to calculate. 500 minus 150 is 350 multiplied by 0.0045, and finally you'll get the resistance at 500 ohms. Comes out very small, closely to the original resistance. Okay, so 258 ohms is what is the answer coming out to be. Okay, so 133, actually not close, quite different. 133 ohms becomes 258 ohms. Is that okay? Everyone, straightforward calculation. Straightforward calculation. Nothing great over there. These kind of questions again asked in JEE means you will see it many times. How about this question? Voltage and current graph for two different temperatures are given. The relation between T1 and T2 is who is more, who is less? Voltage versus current. So what will be the slope? The slope will be the y-axis by the x-axis. Y-axis is voltage, x-axis is current. Voltage by Ohm's law is IR. Current cancels. So the slope is basically the resistance. Okay. So who has more slope? Obviously T1. T1 has more slope. That means resistance 1 is going to be more. Resistance 1 is going to be more. Is that right? And resistance, we know, increases with temperature. I had told you this right over here. I don't know if you forgot this. For conductors, as temperature increases, resistance increases. So that means only one thing is true. If R1 is more, that also means T1 is more. T1 is more. So hence, this is higher, 100%. T1 is higher than T2. Hence, option A is correct. If this has higher slope, this has more resistance, this also has more temperature. So that's why T1 is higher. Option A. Very good, Homedeep, Ganjan, Herborine, Harish, Chitra, Moksha. Yes, capacitors will be coming to it. Guys, I have a suggestion to make. Tell me how it works for you. Instead of doing combination of resistors as the next class, how about we start with capacitors, except for combination of capacitors, because combining capacitors or combining resistors is the same thing. Just one formula changes. For series, it is parallel. For parallel, it is series. Apart from that, the knowledge or basically the method, the process is very similar. So how about we keep a separate class for just combination of resistors, capacitors using KVL, KCL, combination of batteries, etc. as a separate class. Rather, we start off with capacitors. The basic theory, charge on a capacitor, how to find the capacitance, energy stored in a capacitor, all those things. And then we just do equivalent capacitance, equivalent resistance as a separate lecture. That will complete the chapters very quickly. How about that? Do you guys agree with it? Yeah. Let's see, combination of resistors, capacitors is the same thing, whether resistors in series or capacitors in parallel, one and the same logic. It will be very fast, and not just fast. It's not about fast. It's more about, you can study two things together. You can understand how things work properly, and especially when mixed question comes, rather than seeing this here separate, seeing this here separate, and then again reading the entire stuff again and again. It's going to be done very efficiently. Yeah. Yeah, for instruments, we'll have a separate class. Obviously, potentiometer, meter, bridge, Wheatstones, all this. You can have a separate class for that, because that is specific to electrical current. Voltmeter, ammeter, galvanometer, potentiometer, meter, which have a separate for that. Okay. All right. We'll do that. I think that will be better. How about this? Percentage error in measuring the length and the diameter is this percentage error in the measuring of the resistance. They have combined two chapters together in JEE Mains 2024. Resistance is rho L by A, and area is nothing but pi diameter square by 4. Take 4 on the top, 4 rho by pi, length on the top, diameter raised to -2. So that is what resistance is in the power form. Why did I write it like this? Because wherever you want to find errors, you write every physical quantity raised to the suitable powers in the numerator. So therefore, the relative error or percentage error in R will be length's power is 1. So 1 multiplied by delta L by L, percentage or relative. Diameter's power is -2. Always take the positive value, mod value. 2 into delta D by D, percentage or relative. Length has an error of 0.1 plus diameter also has an error of 0.1. 0.2 plus 0.1 is 0.3. Hence the answer is 0.3 percentage. 0.3 percentage, JEE Mains 2024. That's the answer. D for ID Delhi. What a lovely question. Thank you, Anant. Sorry, am I pronouncing it correctly? Anant, with a lot of T's out there. I'm so glad. And be a part of the entire community, guys, not just here. So I'm already there on Telegram with the same handle, Captain Shreyas, where I give you all useful information. No nonsense over there, plus motivation, whatever. Plus, I'm also there on Instagram for little bit chill out, videos. Yeah. Rather than following random, people who are distracting, better follow your influencers who educate you for JEE and NEET. After JEE and NEET, you can follow whosoever you want. You want to follow some actors, actress, you follow them. For now, at least follow us, so that it will help you in JEE and NEET, and it will keep you from distractions, right? Okay, moving on. Electric field is this much, current density is this much, then the conductivity is. Electric field, conductivity, current density. Is there any relationship? I think so. E is equal to rho J, and rho is 1 by sigma Oh, perfect. So conductivity sigma is basically J divided by E. So now I can just substitute it. J, current density is 0.1. Electric field is basically 20. So this will be 1 by 200. So 1 by 200 is B for IIT Bombay? Yes, that is correct. Perfect. Awesome. Thank you, Gunjan. Daily you are present. Why pi d square by 4 comes? My art. What is the area of a circle? What is the area of a circle? Pi r square, no? So what is the radius? Diameter by 2, no? So what will it become? Pi d square by 4, no? So that is why the formula of area, I put it as pi d square by 4. And that 4 in the next step goes on the top. Okay, cool. Awesome. Raghu, almost we are done. Just EMF is remaining, I think. Yeah, after this few questions, EMF is remaining. We'll just do that and that's it. Okay. Wire has length stretched 25%, the percentage change in the resistance. In such questions, this was a previous year question. Be careful. Whenever the wire is stretched, a lot of people think length changes, but do not forget even the area changes. So when you have a wire like this versus a wire like this, the area will change. What remains constant is the volume. The volume is a constant. So area into length is basically constant. So original area was A, length was L. So if final length is 25% more, all right, we'll do one thing. I'll just write area into length is nothing but volume. Okay. So now let me write over here resistance is rho L by A. Instead of A, let me write it as V by L. Let me write it as V by L. So what will happen? It will become rho L square by V. This is perfect. This just tells resistance is directly proportional to the square of the length when you stretch it. When you stretch or basically compress it. This is very important. Many times stretching questions come. People think R is directly proportional to the length, which is not correct. Now think about it. If the old resistance was R, the length was L, the new one will be the length changes by 25%. That means it will become 1.25 times of the older length. Resistance is square proportional, so it will be 1.25 square times the older resistance square proportional to the length. Is that agreeable? Everybody with me? Everybody with me? Understanding this point? Why? Let me know if you guys got this. It is 25% more. That means it will be 1.25 times the older one. 1.2 times the 25 times the older resistance. Older length. So basically you have to square it. So 1.25 multiplied by 1.25. That is 1.25 square times the older resistance. Is that absolutely clear, everyone? Very good. Awesomeness. So what will be the answer of 1.25 into 1.25? Let me know in the chat box. 1.25 into 1.25. How much will it be? R is proportional to R L square. So some student is like, sir, I did not understand it. Okay, check this out. R new by R old will be length new by length old, and this is whole square. What is the new length? 1.25 times the older length because it is 25% more. This is the old length. Square it. New resistance, I don't know. What is the old resistance? It is R. LL got cancelled. So what is the new resistance? It is 1.25 square times the old resistance. So how much is that new resistance? 1.25 square. 1.5625. Perfect, Harborang. Wow. Very good. 1.5625 times of R. So if I now ask you how much is the percentage change in the resistance, the answer will be new resistance, which is 1.5625 R, minus the old resistance upon that old resistance, whole thing multiplied by 100. So 1.5625 minus 1 will be 0.5625 multiplied by 100. R has got cancelled everywhere. You can see that R got cancelled everywhere. So what am I left with is 56.25%. So the resistance will change to 56%. That is the correct answer. Very good. Awesome. Rambi, did you understand this calculation? Why it became 1.25 square? Because it was square proportional to it. So the ratios will be directly proportional to the square of the length. Cool. Shall we go ahead to the next? Yep. Coming to the batteries part, cells. Let's talk about cells now. Now, cell is like you have the mitochondria, the powerhouse of a cell. So, guys, this batteries basically power up the or give energy to the entire circuit. Whenever you have a circuit, you always need to give some energy to these charges so that they can go around different devices, fan, bulbs, motor, this, that. And when they come back, they lose all the energy. So the cell again powers them up and supplies enough energy to go again in the next circuit or the next lap or the next round. So the batteries or the cells, all right, they basically what they do is they convert oops, they convert chemical energy which is stored, into electrical energy. This electrical energy is used for the motion of the electrons. This happens when you are discharging a battery. When you discharge a battery. But when you charge a battery, the exact opposite process happens. The electrical energy gets stored in the chemical form. So this is when you charge your mobile phone. What are you doing? You're using the external electrical energy and storing it in the chemical form. And when you are using the mobile or using a torch, you're using that chemical energy in its electrical form. This electrical energy can be used for doing work in many different ways. Maybe heating, maybe lighting, maybe moving something, mechanical energy, maybe sound, who knows. So it is going into the electrical form. This is what you should know. Okay, magnetism after 1 week or so, 2 weeks. The manner in which you represent a battery is like this. This is how you represent it. And you also show a small resistance here. This is EMF, this is R. This R is also called as the internal resistance, which is present within the electrolytes, that chemicals which are there inside the battery. This is the positive terminal, this is the negative terminal. Remember, this is the positive, this is the negative terminal. Inside that, there is some resistance of that fluid, not that air resistance. This is the electrical resistance that we call it as the internal resistance. Is that absolutely clear? Please bear this in mind. For an ideal battery, for an ideal cell, the diagram will be just like this, because internal resistance will be 0. There is no resistance only which is present inside that particular cell. Keep that in mind. Now, what is this EMF exactly? This EMF of any cell, is nothing but defined as EMF of a cell is defined as, observe this carefully, the work done to move a charge from one terminal to the other, per unit charge upon the charge that you have moved. So the work done to move it from one terminal to the other terminal, that means once across the circuit. If you take it from this terminal to this terminal, that means you have moved it across the circuit upon, okay, you have moved it across the circuit upon the charge, which is basically Q. This is what is nothing but EMF. Now, the top part is obviously in joules, The bottom part is obviously coulombs. So how much joules you take to move 1 coulomb of charge is basically the EMF, and that EMF is obviously measured in volts. So 1 volt EMF is when you need 1 joule of energy to move 1 coulomb of charge once round the circuit from one terminal to the other terminal. Is that absolutely clear? Is that absolutely clear? Yep. Very good. Now, if this much is understood, let's just see the final part of EMF. There are 4 modes in which you can connect a battery. Nobody tells you this clearly. I've seen many lectures. Many people skip these topics. So I'll just do this and then we will, end this class. So stay tuned till the end. And if you have forgotten to smash the like button, do that right now, because I give you complete content in detail from the basics with application of that concepts. Okay. So there are 4 modes of connecting a battery. What are those 4 modes? You take that battery, maybe it has some internal resistance, and connect it to some external resistance like this. This is called as your load. The load might have some resistance R like this. This is the first way you can connect it. The second way you can connect it is you have the battery like this. There is no load at all. You just connect the terminals of the battery. You just connect the terminals of the battery like you might have done it in your childhood. Take a battery and just connect the positive to the negative. What happens? Just write it in the chat box. Something interesting happens there. Third one is where you are taking that battery with that internal resistance and there is nothing connecting only, or you can think there is a load, but that is infinite load. Infinite load. This is the third possibility. And the last possibility is you take the battery, but this time you are not connecting it to a load, rather you are supplying it some current from the opposite way. This is connected to the positive side, this is connected to the negative side of something else. So maybe you are connecting it to the positive, this is being connected to the negative of an external supply, These are the 4 modes of connecting a battery, and any circuit will have only one of these 4 modes, nothing else. This particular mode is called as discharging. This is called as discharging mode because you are discharging the battery, you are converting the chemical into electrical work. Electrical work is being lost in this resistance. The second one is called as shorting. When you short something, that means you are connecting 2 terminals by a wire. You are connecting a wire between 2 terminals or 2 points. That process is called as shorting. Next one, this is completely disconnected. This is called as an open circuit. And this one, you're connecting an external supply to the battery. This is where you charge the battery. Through some external supply. Here, you are basically discharging it. In the case of discharging, there will be some current which will be going here like this. That current will be the total voltage divided by the total resistance, right? It is the total voltage, whatever is there, upon the total resistance. So this is what it will be. If you want to measure how much will be the voltage across the terminals of the battery, VT, the terminal voltage, which is VT, that will be how much current is flowing into the resistance, which will be E divided by R plus small r into R. That is your terminal voltage. Notice how this number or this factor r upon r plus r, this whole factor which you are seeing is always going to be less than 1, because the numerator numerator the numerator is less than the denominator. The numerator is less than the denominator. This also means that the terminal voltage will be lesser than the EMF. Very, very important. What does this mean? If you have seen a battery, something like this, if you have seen these batteries, yeah, these batteries, on that there is a number written, like I can see over here, it is written like 1.5 volts. 1.5 volts. That number is the EMF. If I use a voltmeter and measure it, it will not show 1.5, it will show 1.48. Then you will be like, oh my God, the shopkeeper cheated me. I got 0.02 volts less. But that is not a problem. That is how it is designed. Terminal voltage is the actual voltage you get. EMF is what the battery would have given had there been no external resistance and all those things. That is the most idealistic scenario. So EMF is always more than the voltage which you get across the terminals of a cell. Is that absolutely clear, everyone? Yeah, everyone about this clear? In the next case, when you short it, what happens is this current will be very, very huge. This current will be huge because it will be just E divided by R, but R is small, therefore current is large. So that means the battery discharges quickly. The battery discharges quickly, and as it does, where does it lose that energy? All that chemical energy will go against whom? There is nothing external, it is internal only. All energy is lost as heat. All energy is lost within the battery. Within the battery as heat. So we'll see a lot of heat. So the battery will become hot. If you connect a wire to itself, I mean positive to the negative of the same battery, you will see the battery will become hot, and you will see the battery will be discharged very quickly. So that's how you can discharge a battery really fast, by shorting the terminals. Yes, this is basically short circuiting. So see, a lot of people get confused, sir, what is the short circuiting, sir? See, normally if you might have seen a socket, this is how a socket looks like, your plug point. Okay, maybe there is a electric fan somewhere over here, or there is a bulb or something, some device is there. This is some device. Normally what should happen? This is connected here, this is connected here. What is the meaning of short circuiting? Sometimes these wires get exposed, some rubber cladding, some plastic which is there, which comes out. So this wire might touch this wire. This wire might touch this wire. If these two wires end up touching, that is called as shorting. Shorting means connecting 2 points. What does shorting mean? It is basically connecting 2 points. By chance, if you connect this point over here, okay, that is basically called as shorting. And once that happens, no current will go through the bulb, everything will go here. And once all the current passes from here, there is lot of current. The current increases drastically. It gets heated up. And once it gets heated up, it might even burn. It might even burn. Okay, so that's how fire is caught in case of shorting. Did you understand? In case of cell, obviously fire is not caught because the battery's voltage currents are very low. But in case of your regular power supplies, the voltages currents are high. That's how a lot of energy is there, and it might even catch fire. Next one, open circuit. Very, very crucial, guys. There is no current. Current is zero because there is nothing to flow. What will flow in there? Nothing will flow. And the best part is, whatever the terminal voltage is there, that terminal voltage which is there, it will be E only, because understand, if there is no current, what will happen? That's it. Whatever voltage you measure will be the EMF. This is the most important thing. So when no current flows, very, very crucial, when no current flows through a cell, through a cell, comma, the terminal voltage is the EMF. The terminal voltage is the EMF. Very, very important. Okay, no current, no voltage lost across internal resistance. Complete voltage is the EMF. What an interesting thing. Yes, this might be seen in the ceiling wiring anywhere, Gunjan. It can happen anywhere inside a device, just your wires which are hanging on the ceiling, or even those electrical poles during winds, these wires will touch, short circuit. That's it. Charging. This is slightly opposite. Here you are charging it with an external supply, V external. In this case, the current will go like this. Maybe you can see the current is entering the battery's terminals, and you will see that your V external will be now, it will be now E plus IR. It will be E plus IR. This is in the case of charging. Remember, in the case of discharging, it is exactly opposite. Here your V terminal voltage would be E minus IR. It would be E minus IR. Very, very important. E minus IR. Because there is some drop in that internal resistance. That's why the terminal voltage is lesser than the external, EMF. Whereas when you are charging it, if you want to charge a battery of 1.5 volts, you need to give it 1.55 or 1.6 or 1.7 volts, because some energy will be lost in the internal resistance. This is lost while charging. That's why you need to give it slightly more. That's why you need to give slightly more voltage than the actual rated EMF. Absolutely clear till this point? Everybody with me? Okay, awesome. Now I'll show you one graph over here before we end the class. This is very, very important. Current versus the terminal voltage. Very, very important for a battery. This is what it is. How does this graph look like for current versus the terminal voltage? Take the situation when the current is zero, like a point here. At this point, the current is zero, but there is some terminal voltage. When does this happen? No current. No current happens when the circuit is basically open. That means nothing is connected. I just showed it to you right over here. Open circuit. Infinite resistance. Nothing is connected. No current at all. The terminal voltage is the EMF. The terminal voltage is the EMF. That means this point over here should be the EMF. Everybody understanding this? No external voltage, resistance, no current. So the voltage across the terminals is the EMF, which we just discussed. Then take the other point over here, just this particular point. Then the terminal voltage is zero, but there is current. When is the terminal voltage zero? That will happen in the case of shorting, guys. In the case of shorting, observe over here. What is the voltage difference between these 2 points? It's on a wire. It's on a wire. Guys, there is no voltage difference in that wire. It's a wire. They are shorted. The voltages have been matched. They are the same. So there is no difference. So terminal voltage is zero in the case of shorting. Hence, that is the situation of shorting. That is the situation of shorting, my dear students. So in such a case, the terminal voltage is zero. Terminal voltage is zero. And now any other points over here, you can just draw a straight line. Reason being, what will happen is, if you measure the current and if you see what is, if you measure the current and if you measure the terminal voltage, that terminal voltage will be E minus IR, which is just like your straight line equation, which is just like your straight line equation. Y is equal to mx plus c. Exactly just like that. Y is equal to mx plus c. Got it? So that is why it will be a straight line between any of these 2 points. Okay. In fact, when you short, this current is the maximum current that you can get. That is the maximum current that you can get, which will be E divided by smaller. Okay, that's the maximum current that you can get over here. This is the maximum terminal voltage which you can get over here when you keep it as an open circuit. Is this absolutely clear how this graph looks like? Okay. Harish, I would suggest if there is an urgent test in your school or college, then you can watch JEE channel. But other than that, you wait for me to start the 12th standard chapters over there. Okay, I will be starting there also very soon. Okay. What is terminal voltage? It's basically the voltage between those 2 points. See, when you take a battery, this is your battery, right? This is your battery. If you take a voltmeter and measure it, that is called as your terminal voltage. And that will be slightly less than your actual EMF because of the internal resistance. So that is why usually it is less unless there is no current. If there is no current, this resistance will not play a role because there will be no drop. Then whatever is the voltage here will also be the EMF if it is a open circuit. Otherwise, the terminal voltage will be different from the EMF. Understood what is the meaning of terminal voltage? Thank you, Bishwa. Thank you so much for all the wishes, and thank you for all the wishes on Instagram, Telegram, and all the other places which you showered for me yesterday during my birthday. Thank you so much, guys. Okay. If you're ready for the next class, in the comment section, I want everybody to put up ready for the next, so that I know you guys have watched the class till the end without cheating. Okay. So make sure you put up this particular comment after the session is over in the comment section. We will be starting off with capacitors next class, and then we will do combined class of equivalent resistance and capacitance, all the techniques, then move to magnetism, Newton's laws, all these things are going to come up. Okay, so thank you so much, guys, and I hope you guys understood all the concepts which I have taught over here, right from the basics and with the application part. Okay, bye bye, guys, have a great time, take care. Captain Shreyas signing off. Hasta la vista.